Hi there. This video is going to be about the M62 system that I'm currently working on. A lot of the stuff in these videos may not be in order, but due to the way I'm building it, sometimes things have to be proven before others. Anyway, so let's get started. The main part of what makes this an M62 is the M62 bus. This is 62 pins on the bus. It's got a lot of wiring. Now I have ordered boards for this with 4 slots on it and one of these pin headers on either side, so I can daisy chain them. They've yet to arrive, and and you'll see to the side of the screen here will be the pinout of the M62 bus, and I may have mentioned it in my update video, but M62 happens to be the name of the major motorway, highway, freeway, whatever, near where I grew up. So, which I didn't realise until after I already picked the name, so which was quite coincidental, I suppose. Now the idea is I'll be putting card edges onto prototyping boards like this, and this edge actually come from old Genesis cartridges. And, yeah, you know, a bunch of retro fanboys will be a little upset with me over that. But they were sports games, so they really have no place in computers. If you wanna go play a sport, then go outside in the sunshine and play it. But that's my take on it. Unfortunately, the computer store that I got them from gone bankrupt. Well, they haven't gone bankrupt, but they've closed down now because they couldn't afford to run anymore, unfortunately. But anyway, so the basic card is based on a prototyping card. Yeah, I just received a bunch from eBay. They come in. So that's 2. These are slightly different than the ones I have. They're the same size, but this has an extra power plane on it. If I think on, I will scan one of these in my scanner and put it on to display. Show you. Put one aside. So now you'll notice the first 4 pins either side are pretty much shorted through. That's because they are the same on both sides. Working from the outside inwards, you have 12 volts, ground, 5 volts, ground, and then everything else is different. I purposefully did the it to be symmetrical on the outside, because if you, for some reason, stick the card in the wrong way, the voltage will be right, but the control lines will be all screwed up. But you don't have to worry too much about that because it won't cause any damage. But if you were to put 12 volts on the 5 volts line, then bang, you know, all your chips will be dead. So I'm still working on standardizing the layout of this thing, the physical dimensions. I was actually swinging towards putting the edge on like that, and then having a case with guides on it that I can just slide the cards in. But I'm starting to swing back to keeping them at this form factor, and having slides on this edge and like one over here, like on a case, and sliding them in that way. This will also allow me to do an expansion in the future if I wanted to do for like 16-bit processors. I could just basically just stick another bus in parallel here, and that way it'll still be compatible with the original cards. But yeah, so the big change since my update video was the addition of this onto this. It is already on the board I've had sent off to be made, but I've actually trimmed some pins off either side because I have an IDC connector here, but it doesn't have 62 pins. It has 50 something. I haven't counted it, but I found if I cut this down, I can get the 5 volts in ground, and then all the control pins included. Since I don't need 12 volts for this, and that this is now what will be the front panel board. It frees a slot up. So I've started remaking the front panel card. I haven't shown you the front panel card yet, so I will show you that before I move on to them. Okay, so this bodged mess is the front panel card, and what it has here, let's get some point. Right. So we have the data bus here, the switches for the data bus, and LEDs for the data. Sorry, it's written right there. It's the address bus, and the switches for the address bus, so I can manually set the address. And the same goes for the data here. What we have here is I have a bus request button, a switch, and a bus acknowledge LED. So basically, I switch that into bus request, which pulls it low, and when the processor is releasing the bus, it will light the LED up. It's active low, but I make the LED light up when it's active. So. And here we have the memory request line. I originally wanted a button where I just push it and it'll deposit the memory, and push it and it'll read the memory, but it didn't work. But oh well. So yeah, so I have the memory request line, and I also have the read and write lines here. So when I have it in bus request mode, and the bus request comes on, I can then say I want to set my address in there, and I hold read down, and I bring up memory request, and the contents of that memory location will appear on the LEDs. And the same thing can happen with the write. Use the write button, but it will write whatever's written on the data switches to it. Okay, and then I also have the obligatory reset button. And next, there's a bit of circuitry here, which is the single step circuitry, and I will tell you more about that in detail now.
Okay, so here is the single step circuit as I am currently using right now. The other variation is actually to use 2 NAND gates to do the stepping. The other circuit is exactly the same except this bit here, but this is the circuit I'm using right now. I opted to use the Schmidt triggers because I thought it'd be cleaner. I've not proven that yet, but you know, this does work. I haven't tried the other way yet, though I may have a go at that sometime, because that way I can cut down on using this chip in the circuit. I can just use all 4 gates of the SIM400. So, okay, so where should we start? Okay, this switch puts it into run mode or stop mode. Stop mode is what allows you to single step through each command, also each instruction, and run mode means the processor will just run as it is without any without being stopped by the circuit. Okay, so we'll talk about it being in the stop mode for now. So obviously we don't need to cover the run mode. Yeah. Okay, so when this is in stop mode, this is pulled up, and then basically this will act as an inverter. Anything in here will be inverted. Okay. Right. Okay, upon powering up, this chip will be in reset mode, which means the Q state will be 0, and the not Q therefore will be a 1. And 1 coming out and inverted will assert the wait state, the wait control line, which obviously will put the Z80 into a wait state, so nothing will happen. When this gets toggled and a clock pulse gets asserted, not asserted, gets triggered by the circuit, the contents or the state of D will be transferred to Q, and obviously D is pulled high, so Q will then become high, and not Q obviously will be low, and therefore this will be inverted to a high, therefore it will pull it out of the wait state and it will allow the processor to run. So what the processor will do, it will continue fetching the rest of the operands for the instruction it just loaded upon startup, which is where it was stopped, and then once it fetches the next instruction, it will then bring M1 low. And this circuit here is a single shot multivibrator. Basically, when the M1 goes low, it will then trigger it, and therefore it will create a high pulse. So this will invert it into a low, and this circuit will not trigger again until M1 has gone back to its high state. Anyway, the pulse here will then reset this this flip-flop, setting Q back to 0 and not Q back to 1, and basically making the processor wait again after it's just retrieved the next instruction. And this is how the cycle works. So you tell it to step, it releases the processor until the next instruction retrieval step, which is the M1 cycle. And yeah, that's how the single stepping works.
This will eventually be moved to the processor card, which I'll show you next. And obviously there's the switch for the running and stopping, which controls the gate. And that's my step-in toggle. There's a connector I put here, which goes to a button on a wire. Because I found toggling this sometimes waves this, and these are recycled connectors. The pins are corroded, so and I don't want to use my new ones until I get my boards in, since I've only got 4 of them right now. But yeah, I'm redoing this board. I originally had 7.4, these LSs, well, some of them are HCTs, but anyway, I had some 7.4 244s working as a buffer to drive the LEDs, but I'm scrapping that in favour of using transistors, since I got thousands of, at least hundreds of NPN transistors. You know, these chips, not that cheap. I can't remember exactly how much they are, but I just bought some, and they weren't cheap. It's about $1 a piece, $1.20 maybe. And really, they're useful for when you want to isolate the bus completely, and selectable. But these are held on all the time, so you can always see what's going on the bus, which it's a bit of a waste, since I could just use a transistor for each line. Yeah. So anyway, so yeah, the single step-in circuit will eventually be moved to the processor. This here, I have an NMI switch to convert the non-maskable not convert, to trigger the non-maskable interrupt. Okay, so that's called the processor card. Okay, so this is my Z80 processor card. It's got my 4 MHz clock here. I have a an interrupt and an NMI switch on it. So the NMI does the same thing as the other one does. The interrupt switch, I've not really played around with interrupts yet on the Z80. It's got a weird structure associated with it that I'm not quite read up on it. I've got to continue reading up on it. I have a Smith trigger here to smooth out the reset and the NMI and the interrupts. So that way it'll only trigger once rather than like bouncing. It bounces. Sorry, it's a bounce circuit. And what I got here, this is where where I'm experimenting with the bank address registers that I've added on the bus, which you'll see on the bus right here when I bring it up again. You'll see the BA0 to BA7 is the bank address, and this is where the circuitry will go. I did make a module to test it out, but it's not very good. I do have some other chips to try, so when I eventually get that working perfectly, it will go. The circuitry will reside on the same board as the processor. Like, I'm going to be redoing these boards when I get my proper edge connectors and stuff in. Yeah, these are just prototypes, just to try out things to prove my designs. Okay, so let's see what's next. I'll show you the Rom and Ram board. This is the main Rom and Ram board. Now, if I show you the memory map right here, now you'll see there'll be bank 0, 1, 2, 3, and sorry, bank 0, 1, 2, 0, 1, 2, yeah, 0, 1, 2, 3. So 4 banks, and each of them will be 16 kilobytes size for the banks. Now, I've got the 2 memory sockets here. There's switches here, and written on them is the up position is 0000 hex, and the bottom one's 40000 hex. Basically, up is bank 0, down is bank 1. So I can select the RAM to be in bank 0, which is where the system boots from. In conjunction with this, I can hold it, and I can type my code directly into the RAM and then let it run from there, which I have done, and it looks okay. I will show that. Hopefully I'll do it in this video. If not, I'll definitely do it in the next video. It's my address decoding. And yeah, see, these jumpers are for the extra address pins for the ROM, which I don't use, so I could put different programs in and just select between them, but I'm not really using them. They're pulled down, so I'm only using 16K of this ROM, which some would say is a bit of a waste, but yeah, it's not like it's actual PROM, so but yeah, that's 64. No, so that's a 32K RAM, so I'm only using half of that right now. And as you see in the memory map, which I'll show up again, the top 2 banks, I'm leaving that open to be whether it could be used as 2 banks or just as one great big bank that's selectable by the bank address. But definitely the top bank, bank 3, is definitely going to be switchable. Bank 1 might be an extension of bank. Sorry, bank 2 might be an extension of bank 1. I don't know. That's user definable, I suppose. I suppose I should show you my work in progress of my new front panel card. So, like I said, I had this. This is from an old magneto-optical drive I took apart years ago. I found this in the garage. This bit of cable. Only had one end left on it. So I thought I'd use it. So I've gluing it to the board. Not gluing it. Electrical glue. Solder it to the board. And I put some transistors in here. Now, in my wisdom, I realised that 3-hole transistors would start bunching up and wouldn't properly fit, so I had to switch to surface mounts. Now, as you can see, there's surface mount transistors soldered onto those headers there, and then I have a bunch of resistors underneath going to the second header. So the idea is this first header goes to switches, which will be on the front panel when they finally arrive, and this header will go to LEDs, which will also be mounted on the front panel. I have a sheet of aluminium somewhere that I'm going to be using for the front panel. But yeah, this is the work in progress. This is just a ground wire and an LED. I basically made sure each transistor is wired up properly and drives the LED correctly in order to make it work. So I'll eventually have the same circuit doing both data and bus address pins. These are all NPNs because they're at active high, and I'll be doing a bunch with PNPs, active low, for the control lines like M1, read write, that kind of thing. So yeah, that's what they'll be for. So yeah, so this is a work in progress. And one board that I've been playing around with a bit, it's still a bit flaky, needs help. Needs software configuring, is my Arduino card. This allows me to debug the system. I can read and write the RAM, read the ROM, any address, pretty much like this, but not manual. I can read and write in hex. I can fill a memory space, I can control the processor, I can put it in reset, bring it out reset, trigger an MI, and all sorts of things, pretty much what could be done with this, but with a little bit, just by typing instead. And also, I got a selection on here, the switches here. The first one will be bootload from SD card, basically on startup. It'll read these switches on startup. If this one is selected, then it will load a file off the SD card. I think it's M62 boot.bin, I can't remember now. It'll load that and copy it to address 0 until the end of the file. And this second switch here is to whether or not to release the processor on startup. If not, it'll hold it in reset mode. And so basically, if it's released and if it's in bootload mode, it'll bootload and then it'll just let the processor run. If that's put down, then it'll bootload the processor and bring up the menu and just wait for me to tell it to release. But yeah, it kind of works. It does read and write the memory. It copies the memory and stuff. And yeah, about it working, so I'm happy with it. But like I said, there's a few glitches in it here and there. It's not that much wiring. I had to put resistor array, otherwise it confused. But yeah, that's the that's the status of the boards right now. So I hope to get the bank addressing tested and done, and make sure that works, and then I can incorporate it on the new board. Hopefully stick it on this one, or make a fresh one with the new connectors when they come. Then I can start properly doing my development. Now we can start fitting the thing in a case. But anyway, I'm going to go set it up, and I'll be right back and I'll show you in operation. Okay, so what I'll do is I will show you the operation of the front panel without the processor in. So we'll start off, we'll stick the memory card in. Right. Everything's off right now, so all the lights are off. And then we'll stick the front panel card in. And then I will turn the power on. So we're at 5 volts on the power supply. Where are my tweezers? Yeah, should have done this bit. There we go. Tweezers. Okay, so right now, let's see. The ROM is at 0000 right now. The RAM is at 4000 hex. Not technically 4000, but I don't know. Can't wait till I get a proper case for this. That way, it's not moving around. Plus, then I won't have a lot of switches anyway by then. Okay, so let's have a read of the bus. So it looks like it's lit up, but it isn't. I can make it look nicer for you. Okay, so I hold the read line down, and I put that on, and okay, so one, two, so it's 3-1 in hex. That is a load stack pointer, and then I will go to address 1. Can you see that okay? Okay, and then we'll read that. That's FF. Okay. Then we'll go to next address. And that is 7F. So, in principle, in summary, so that is 31FF7F, which means load stack pointer with the address 7FFF, which is the RAM top in this case. And then so let's see, the next address states, okay, and that is 3E. 3E, I believe, is load accumulator. Okay, next address. Sorry, I've got my hands in the way. Load accumulator with. Oh, that's 4D. And 4D is it's a capital M in ASCII. I use that all the time. Okay. Oh. Okay, so yeah, see, I'm blocking the camera all the time, which is not good. I'm either blocking the camera or blocking myself. So the next address is 32. 32. Stores accumulator. Where are we storing it? Zero zero. 400. 4,000. So store so it's 320040. So store the accumulator at hex 4000, which in this case is the first address of memory. Yeah, these switches are really fiddly. That's all I had at the time. Yeah, that is C3, which is jump. And where are we jumping? Uh, 8. Some. So jump to 008. So basically loop around where you are. So yeah. So the whole operation basically states load 4D into the first address of the memory, then just jump back to the jump command continuously, so loop forever. Okay, so now in order to write to the memory, looks out the way. Okay, so our RAM resides at 4000, so we're now at the address 4000, and if I read from it, it should be somewhat random data in there. There. See that? Yes. Somewhat random data. But now if I write, you can see address is set as zeros right now, so if I write 0, then I read it again, it's all zeros now. So I could set the bit pattern on the data. Okay, and I'm going to write that. Let's write that, and I've got to clear these again. And if I read, it should be the same pattern. Yeah, there we go. That's how that works. So imagine keying in a program just using tweezers and these switches. That'd be annoying. Might be tedious doing the switches on the panel, but it'd be certainly a lot easier than this. Okay. Next, I will show the processor running. Okay. Right, I've got that off now. So let's insert the processor card. Okay, and I'm going to stick it in run mode and just let it go. I'm going to turn it on. There. Now that is going like crazy. You can't see it, but it's happening. So if I stick it in stop mode, stop. Stop it now. There we go. Right, so if I, yes, it's running right now. And then I stop it. Let's reset the system. Oh, I know why it's going crazy. I still have the address 4000 set. It's trying to run from the RAM. So let's reset that. Okay, as I previously demonstrated with the bit of video when I'd shown you the stepping, it will show you, it'll stop at the M1 state, and this is where it's actually loaded the first instruction, and this is where it's loaded 31 31. So then when I step to the next instruction, So it's loaded FF. Then sometimes it skips to the next instruction rather than showing the next operand. And then, but it basically steps through. And you see here, it's looping. Sometimes it will jump to a different address because I think it's because I'm wobbling it so much it's interfering with it. But if I release it here, you'll see it's staying in the same area because it's constantly loading the jump command and staying right there. So, stop. So now if I hit NMI, step it. Now the first thing it does is actually it puts itself on the stack and then goes to NMI and then it'll put itself in a loop. And it's reset for some reason. Because I'm wiggling it, that's why. That's why I want to rebuild this on a proper backplane soon. So, what the system did is initially it wrote 4D to address 4000, and when I triggered NMI, it actually writes 4D to 4001, and then stays in the loop there. That's what was happening there. So, let's examine the memory. So, I'm going to go and put it in bus request mode. And I have to set the processor to let it know that it's the bus request. So now the process is halted. The buses are all high impedance. So now I would like to see what's at address 4000. So let's do a read 4000, and what do you know? It's 4D. You can see that it's 4D. So let's see what's in 4001. Didn't quite work, but I think that might be down due to the flaky wiring. Or maybe I don't have the code for that in there. Oh well, I will dump the ROM later and see. But yeah. Okay, so that's that in operation. I will next. I'll show you the Arduino code running, but unfortunately, I'll have to unplug this camera so in order to use the USB port. So I will see you in a minute. Okay. So let's clear the output. Alright, so here we have the serial terminal from the Arduino. Question mark will bring up the menu, so-called menu, and the processor currently in hold right now. It's held and reset because that's what I selected to it. I haven't selected the bootloader. So right now the ROM is at 0000 and the RAM is at 4000. And if I bootloaded it, it'll try and write data to the ROM, which it can't do. Well, I can try, but it won't. Okay, so let's dump the ROM and see what's going on. It's a little slow, yes. I need to speed it up. Yeah, I seem to have put the NMI stuff in the wrong place. Yeah, well, doesn't make a difference. Either that or it's a mistake with the software, I don't know. But I know the first line is correct. But basically that's what we read when we did the toggle switches. And oh, I gotta fix it in the dump mode. So basically now if I want to read address 4000, it's set as 0 right now. And So let's release from the reset and let's hold it. Right, so now let's read address 4000 again. And if this all worked correctly, this should be 4D. No, it did not work correctly. I wonder why. Okay. Hold. Let's read 4000 again. Okay, let's read 4001. See it. Yeah, it worked. 4001. It has shown it actually did work. So we can prove that. Let's write to 4001. Let's write FF. Okay, so let's read 4001 just to make sure that it read correctly. Incorrectly, yeah. So that's there. So now if I release and do an NMI again, and then hold, and then read 4001. 0. All right. Let's release, reset, NMI, hold. Yes, the Arduino software is very flaky on here. Okay, let's reach 4000. Yeah. It sometimes works and sometimes doesn't work. It's hit and miss. I don't know if it's the wiring or my software in this case, but it's a work in progress. And so I'll show you what the boot loading's like with this. So so I have to power off the system, which means plug in the Arduino in this case because it's powering the board. And I'm going to be changing the jumpers on here. There we go. So the RAM is now at 4000 and the ROM's at 4000. Right. Okay, I started the bootloader on. Let's plug it in. See activity on the SD line stating that it's doing something. I'm going to have to gets upset when I change serial ports, that's all. Okay, it's now flashing the Arduino. Okay, there we go. Just telling me what it's writing. It's going to read the entire file that's there. There we go. So now it's ready. So let's place a dump. Let's dump the memory. Show you what's in there. See, anywhere after 6A is all just going to be random gibberish. So let's write 006B 00 FF. So I'm just gonna. Oh no, in examine mode still. Yeah, I need to sort the menu system out. 6B00 FF. So I'm gonna fill 255 bytes after from 6B onwards with zeros. Okay, so now let's dump. Should look a little cleaner and you'll be able to see exactly where the code is. There we go. And yeah, so basically do the same thing. It'll put 4D, but this time it'll put it address 8. So 8. No, address 800. Sorry, 8. Yeah, 800. So X. So let's release this. Oh, and hold. Read 080. See, it's a little a little flaky, but it's a work in progress. Yeah, so I'm going to call this video for now. If you go on my website, hopefully all the information will be all on there. I do intend to make everything public, so if I've missed anything on there that I've mentioned in this video and you don't see it and you would like it, then just drop me a line and I'll definitely make sure it's up there for you. But this all should be available. And well, yeah. So I'd like to thank you for watching, and hopefully this will give a good insight, and hopefully my stuff will come in very soon and we can start getting into the proper boards being made. I would like a case with a front panel with proper switches and proper clean backplane headers, so we can start doing these things without shortings and crosstalk and corrosion, crappy connections. But they're on a slow boat from China right now, unfortunately. So it should be here soon. So thank you again for watching, and I'll see you again next time. Okay, goodbye.
Thank you very much for watching my video, and if you like what I do and wish to contribute to me, please visit my donations page or consider supporting me through Patreon. I'd like to say thank you to those that have donated, and I'd like to shout out to my patrons. Without your help, this wouldn't be possible. Thank you very much.